Well, it's a great pleasure to welcome Wolfgang Ziller, who will speak on a variational approach to prescribing the Ricci tensor. And just a reminder, the meeting is being recorded. Feel free to unmute yourself at any time if you have questions. So I'll turn it over to you.
Okay, do you hear this? Do you hear this noise when someone logs in?
Yes, I just turned it off. Don't worry, sorry.
Yeah.
Do you know what causes that?
I don't know.
I already turned it off. Don't worry.
I
Okay,
turned it
fine.
off. Good. I wasn't sure how to do that.
Okay, let's start now then.
Yeah.
Okay, thank you very much for the invitation. It's a pleasure to talk in this seminar that I enjoy attending. So this is a joint work with Artem Pulemotov and discusses the problem of prescribing the Ricci tensor. So let me first discuss the setup and some known results. So one would like to understand the Ricci map, Ricci curvature map, which associates to a positive symmetric 2x2 tensor, its Ricci tensor, which is again a positive definite symmetric 2 tensor. And one would like to understand this map. What is the image, for example, or is it diffeomorphism, a local diffeomorphism? So a question of this type is what I would like to discuss. And there's some classic results. Maybe the first one is due to Dennis de Turk in his PhD thesis. He proved that this problem also always has a local solution if the tensor T is non-degenerate. But there are counterexamples if you allow degenerate tensors T, not even locally. So locally one can always solve, but globally, of course, is a problem. One is not always able to solve, and we will see under what conditions one can do this and to just understand the reasons. Here's another result of de Turk and later on independently by Hamilton. They proved, so they made the point that one has to modify the problem a little bit. Namely, if you take a metric on a surface, on a compact surface, then for every tensor T, positive definite tensor T, so every metric T, there exists another metric G, unique up to scaling, such that Ricci G is equal to C times T for some constant C. So both G and the constant C is unique. Of course, G is only unique up to scaling, since conformal metrics have the same Ricci tensor. But also for the tensor T, for the prescribed tensor, I would like to allow a kind of scaling. So the problem should be modified to study the Ricci map, modulo scaling on the left and on the right. So scale the metric and scale the tensor T. So in other words, I would then form.
A ver, lo voy a escribir mejor.
Pardon? Yes? Was there a question?
No, I think that was just an audio.
Sorry.
Yes.
There.
So given a tensor T, which we assume to be positive definite, the question is, does there exist a metric G and a constant T? So that Ricci is equal to C times T or some C. And so another one of my favorite theorems, also by Dennis and together with Coiso, he showed that this Ricci map is a local diffeomorphism, modulo scaling, if the metric itself is an irreducible symmetric space. Of course, for the metric itself, if T is G0, you have a solution, just a symmetric space metric itself, since it's Einstein. But it says it's also a local diffeomorphism. So for nearby tensors T, I can also solve the Ricci equation. And this is typical, this sometimes holds for Einstein metrics. So when you reduce a symmetric space in Einstein metric, and this property of being a local diffeomorphism sometimes holds for Einstein metrics. And there are various theorems in this direction, which I don't want to discuss. Before I start with the aspect that I want to study, let me mention some previous work that people have done. There, mostly in under two different assumptions of symmetry. One is there are 3 papers where you assume that you have a COM-G1 metric, so a metric where the symmetry group has a one-dimensional quotient, and a sequence of papers where one assumes that the metric is homogeneous. one then tries to understand under what conditions on T can I solve the Ricci curvature equation. So the aspect that I want to study for this problem today is a variational aspect, which is what the title says. So in fact, I will compare two different problems that are related with certain similarities, but certain differences. One is the Einstein equation, and the other is a prescribed Ricci tensor. So C will be the constant in the prescribed Ricci tensor, and E will be the Einstein constant. So I look at the space of all G invariant metrics. So I call that space M. And so this is a hypersurface in a finite dimensional vector space, the set of all G invariant 2x2 tensors. And I put this constraint on the metric. In each case, a different constraint. So for the prescribed Ricci curvature problem, I require that the trace of the tensor T with respect to G is equal to 1. And I look at the subspace that satisfies this constraint. And for the Einstein equation, I put on the constraint the volume is equal to 1. And then it turns out that the solution to this kind of Lagrange multiplier type problem are precisely the metrics I'm looking for. So I restrict the scalar curvature so I'm associate here to every metric the scalar curvature, right? That's my map. I restrict it to these two subspaces, MT or M1. And in each case, the critical points are precisely the Einstein metrics. And one can see this, for example, if one looks at the gradient of these functionals, they look like this. So for the volume 1 constraint, the gradient is given by the traces Ricci tensor. So here you can see the gradient on the right-hand side is this form. It vanishes when Ricci is a multiple of the metric. So that's the Einstein condition. And for the prescribed Ricci curvature problem, it has a similar form, but now you add a multiple of the tensor T. So again, you can see the critical points are precisely solutions to the problem I'm looking for. Because this form right here of the traces Ricci tensor is well known to be the gradient of the scalar curvature function in the space of all metrics. But now I have a constraint on there, the trace 1 or volume 1, and that of course puts this kind of Lagrange multiplier into the gradient. So what I'd like to do is I'd like to understand the global behavior of this as a variational problem, and try to use the gradient flow of these functions to produce critical points. And then, which in particular means I'm producing solutions of the problem I'm studying. But the aspect I want to study here is the global behavior of the functions. Here the first observation that one makes, this is something that Mackenzie Wang and I discovered in the 1980s for the Einstein curvature problem. The behavior of these functionals, in fact, in both cases, is controlled by intermediate subgroups. So here my homogeneous space is G mod H. That's my fixed manifold, and I want to look at the scalar curvature function. Now look at intermediate subgroups, and then I can do the following. I can form a Riemann submersion. So I form this kind of vibration here, which so that's the important vibration now, right? The base is G mod K, the fiber is K mod H, and the manifold I'm studying is G mod H. I put a metric on the fiber, I put a metric on the base. So this is a Riemann submersion. I can always do this. And now I scale. So it's kind of a well-known trick or procedure one does for this kind of Riemann submersion. You scale the fiber and the base. So here I will multiply the fiber by T and the base by S. Okay. Then I vary T and S. Now it'll look, this is called a canonical variation of a Riemann submersion, well-known kind of method for constructing examples. Right? And for this canonical variation, the form is also well-known for the scalar curvature. This is a scalar curvature of such a canonical variation. So one can now study, well, when does it go to infinity or to 0, and look at the behavior as one of these variables goes to infinity. But I have to do this, of course, under the constraint. So on the T and S, I now put the constraint, and I want to see what happens with the scalar curvature. Typically, I want to understand what happens when I go to infinity. So here's the Einstein case. So I have again my formula for the scalar curvature and normalize the volume to V1. So I put this constraint right here on the metric. Right?
Sorry, Wolfgang.
Yes.
The T tensor is 0, right?
The T tensor.
The second fundamental form. They are totally geodesic, right? The fibers.
All the fibration, yes. So for this Riemann subversion, the fibers are totally geodesic. So its T tensor vanishes. Because I want to prescribe the T tensor, so that's a different kind of tensor. But the fibers.
Yeah. Sorry. I got
That's okay.
confused with the notation.
And this, of course, this kind of construction produces many examples and counterexamples. Okay. So now I want to put on the volume constraint. So I set the volume equal to 1. And then the scalar curvature form has this kind of form. And now we can make two important observations. So the first one is that if I let t go to infinity, then the scalar curvature also goes to infinity if the scalar curvature is positive, if the fiber has positive scalar curvature. So this functional tends to go towards infinity as I go to infinity in my space of metrics. That's the first observation. And the second one is that if the scalar curvature of the fiber is 0, then the scalar curvature goes to 0 as t goes to 0. So I'm shrinking the fiber to 0 here. I also let this t parameter go to 0. So I'm shrinking the fiber down to 0. The limit will be a metric on the base. I'm at infinity in the space of our metrics. And these kind of two behaviors, goes to infinity or goes to 0, that's an important feature of this kind of function here. In particular, it's almost never bounded from above or below. Okay. So the goal then is to understand what happens with superlevel sets. So when the scalar curvature is greater equal to A, can I understand the geometry or the topology of such superlevel sets? And it's natural to look at such superlevel sets since the scalar curvature is not bounded from above. And this kind of feature that they go to infinity for subgroups, that's supposed to kind of tell you the crucial behavior of what happens. So all this was an observation that Mackenzie and I made in the 1980s. So what's the analog of this for the prescribed Ricci curvature problem? So just taking the scalar to MT. So now I put the constraint here that the trace of the tensor T is equal to 1. And again, I have this metric on the fiber, the metric on the base, and then the formula looks like this. So it's important here that I use as a parameter not S, but the inverse of the metric 1 over S. And I'm going to let that go to 0, the inverse. You'll see in a minute why that is convenient. And here get the formula for the scalar curvature. It doesn't blow up. That's the first observation one makes, unlike in the Einstein case. In fact, it has a following behavior. I'm going to let alpha go to 0. So that means I'm expanding the base to infinity. T is my fiber, T goes to 1, and S goes to infinity. Okay. Then you can see that the scalar curvature of this one parameter family of metrics goes to the scalar curvature of the fiber. So that's the important feature that we have to look at, or one of the important features we have to look at, that there are limits at infinity in the space of all metrics. And these limits are given by the scalar curvature of the fiber of one of these homogeneous vibrations. So that's the first important observation. Of course, then I also have a second term right here, which is very important. Namely, it says that the derivative of the scalar curvature as I go towards infinity is given by the difference of the scalar curvature of the fiber and the base. So we're going to see later on whether this derivative is positive or negative. That has an influence on the problem, on the behavior of the problem, and on solutions. So these are the two important things. Scalar curvature of the fiber, one needs to understand, and this difference of the scalar curvature of the fiber and the base. Okay. Let's take a look at an example where one can see these features both in the Einstein case and in the case of prescribing Ricci tensor. Sorry. First, comment I forgot to make is that so the scalar curvature, it's not hard to see, the scalar curvature is always bounded from above, unlike in the Einstein case. So that's a very different feature. And what we'd like to understand then is, well, since it's bounded on from above, does it assume it's supreme? And if it does, of course, that's a critical point, and that will be a solution to my problem. So two different kind of questions one asks in the Einstein case and the prescribed Ricci tensor case. So here's the example I want to look at. It's a flat manifold, S23 mod T2. And here one has three intermediate subgroups. Remember, I need to study the intermediate subgroups, which are given by block embedding. So I put a U2 in a block. Here's A and here's that A bar. Here's 0. So that's one of my U2s. Okay. I can put this in three different ways into block form. I get homogeneous fibrations. I get S2 fibrations over CP2 in three different ways. And I will try to see what happens, for example, when I shrink the fiber to 0 in the Einstein case. And here's a picture. So remember, so there are three different U2s that lie in between, and the scalar curvature goes to infinity. You can see it in these pictures here. You can also see that there are some critical points, some setup points here, here, and hidden over here. These turn out to be Kähler-Einstein metrics. And I would like to understand why these have to exist. There's another critical point in the middle here, which is a binary metric, but it turns out that doesn't have to exist for any kind of topological reasons. Okay, so that's a typical picture I want to understand and look at for the Einstein case. And here's a typical picture for the prescribed Ricci tensor. So I'm setting the trace equal to 1. That's my constraint here. It's bounded from above, the functional. So it's bounded from above. In the picture on the left here, you see a picture of the graph of the scalar curvature in the metric G. So here's the scalar curvature of the inverse of the metric. And here's a metric for the same tensor T. So here I'm prescribing three different tensors, right? T1, T2, and T3. And you get three different graphs, of course. In this picture for G inverse, I see the whole space of metrics. This line here is at infinity. This line is at infinity. And here in the scalar curvature, it goes to minus infinity. Here, infinity is somewhere in this direction. It's a little more difficult what the global behavior is. So I like to draw this picture in terms of inverses. It's also easier to understand algebraically. So here's another example. We have a set of points. So here, of course, we see the global max here. That's my global max here. Here's an example where there's no global max in the last one here, no global max. Here's an example where we have a set of point. So this kind of feature that you can set a point, that you can get set of points wasn't observed in the previous kind of work. So this is something new that we want to understand and prove the existence. Okay, I'm going to come back to these pictures a little bit later after explain a few more things. So two results for Einstein metrics, global results for Einstein metrics for the existence of as critical points on the functional. The first one is due to Christoph Böhm, Mackenzie Wang, and myself. And here we look at the set of intermediate groups, and we call that the graph. So, which is means the following. So you have one group inside another group inside G, and then a group as a vertex. They're inside each other, I connect them. Okay. So that's a simple kind of graph. If I have another group in between, then I might have another vertex in the third group. This one here also sits inside K3, inside G. So from a graph like this, of course, this graph could have several components. And the theorem says that if there is more than one component, then you have a critical point. And it has co-index 1 in the non-degenerate case. So this was conjectured by Mackenzie and myself in the 80s. And we finally proved this. And the proof involves some difficult analysis, hardcore analysis, collapsing theory by Cordy and Einstein, in order to prove a compactness theorem, compactness property of this function. But that's a different story. Gustav Böhm continued this kind of subject, and he constructed a simplicial complex. So if I have three groups, one containing the other, like in the previous picture, I can fill in a simplex. If I have more groups in between, I might get some higher dimension simplices. If the simplicial complex that I construct in this fashion has topology, then I also get a critical point of high coordinates k. So one gets saddle points. One can expect lots of saddle points. And there are many examples that satisfies the requirements of this theorem. So Christoph in his paper gave a wealth of examples where one gets critical points on this kind of topological consideration, variation calculus. Okay, so what's known for the prescribed Ricci curvature in this context? Okay. Yeah, I wanted to first look at the graph theorem in these cases here. Intermediate subgroups are 3 U2s we discussed before. And so I get 3 components. If you want to, in this picture, I could go from one component to the other one, produce a saddle point over here, from here to here, produce a saddle point by going this way, and the third one by going from here to here to infinity to get my third saddle point. So this is again SU3 mod T2, the flag manifold. One on the right hand side is a symmetric space, that's SU2n, not SPN. The graph in this case consists of 2 vertices, so 2 groups contained in each other. Only one direction going to infinity, since the graph has only one component. And this metric right here is a degenerate critical point, and that's a symmetric metric. So the symmetric metric on this kind of simple symmetric space, irreducible symmetric space, is a critical point, of course, but it's a very degenerate nature. And there's no reason for it to exist from the viewpoint of calculus operations. I can easily modify the scalar curvature function and it disappears. Okay, for the prescribed Ricci curvature problem, I do the following. So remember, we had this formula that scalar curvature of a canonical variation looks like this. And I have this kind of property that I go towards the scalar curvature of the fiber when S goes to 0. So therefore, I maximize simply the scalar curvature of all metrics on the fiber, K mod H. And that's my number that I associate to the subgroup K. For the derivative, I take the difference of the scalar curvature on the base and fiber, so I maximize all the scalar curvature of the metrics on the base G mod K. So these are some basic constants associated to every subgroup that lies in between H and G. So there's more structure in this kind of problem, and has these kind of additional invariants for each subgroup. So here's a theorem that we proved, kind of the analog of what I discussed before. So when do we get a global maximum? Well, that's the question here. Well, so you look at all intermediate subgroups, and then there exists a subgroup for which this constant alpha k is the largest. Remember these alpha k's, there's a scalar curvature of the fiber. That's the limit at infinity. So here I'm looking at the largest level at infinity in my graph. And I require that its derivative is positive for that particular suborder. And then it's maybe not surprising, well, in that case, since this is the largest limit, if this is increasing from there, it should give you a maximum. And that is the case. Okay, so this supreme is achieved, it's a global maximum, and therefore a solution to the problem. But proving this is quite difficult. So this looks intuitively natural, but proving it is a totally different kind of story. So in these pictures here, you can again illustrate this. So here are my 3 levels, 3 alphas. This is again SU3 mod T2. The main one is the largest alpha, and it has positive derivative. These 2 also happen to have positive derivative, but that's irrelevant. To reach my maximum, I simply go from the largest alpha to the top, and I get my critical point. So that's a typical kind of picture that illustrates what we're talking about. In this picture here, I again have 3 alphas, this one, and this one, corresponding to these three U2s that lie in between H and G, and either row is negative. So the critical point, the supremum, is assumed at infinity, if you want to. And therefore, of course, there's no global max. But nevertheless, there's a setup point right here. Okay. And the basic question is, how can I prove that this setup point must exist? Okay. And so what one would like to do is similar to the Einstein case. I'd like to say, take a curve going from this point, going up to this point, and start moving it up with the gradient flow and tighten it, and until it becomes a curve which is it's along like this, goes along the ridge, remains hanging on the critical point, goes up here. That's kind of the goal. But this kind of functional does not satisfy the kind of compactness condition that is that holds for the Einstein case, for the Einstein functional, and therefore this is more difficult. But we can prove this in the case we're looking at here. And here's a theorem. So it's this again, the flag manifold. So the flag manifold, the metric depends on three constants. So one decomposes the H perp, the orthogonal complement of the subalgebra. So you have H inside G. Into reducer summons. It depends on three different irreducible summons. The metric has three constants and the tensor T has three constants. In terms of the three constants Ti, I'd like to see when can I solve the problem. And this first part here, the existence, was done by Gold and Pulemotov in 2018. So they proved that this condition here on the Ti's, on the relative size of the Ti's, if that holds, then there's a global maximum. Okay. And what is new, what Artem and I proved last year, is that you also can get setup points. If one inequality doesn't hold, if all three holds, then you get a global max. If even only one of them doesn't hold, then you get, if only one of them doesn't hold, then you get a setup point. So let's look at what that looks like in the space of all tensors. So here's a picture. So I normalize to set T1 equal to 1. Then I have a function in the plane. I draw a picture of T2 and T3, or the tensor T. So that's my prescribed tensor T here. And here I draw the picture of when do I get a max saddle point or no critical points. So in this gray region, that corresponds to the max. So here I get a global max in this kind of triangle here. Okay. And the saddle point exists in these kind of pink regions. There I get a saddle. And so that's under these conditions here, the conditions that are described in the previous theorem. Part A gives you these global max in the triangle, and part B gives you the saddle point in these infinite regions. And in this
Wolfgang, I'm sorry,
yes?
you mean T1 is equal to 1 here, yes?
Pardon? Yes.
T1 is equal.
Thank you. In this white region, we expect no critical points, although we didn't prove that. But just what happened. Am I still connected?
We've lost your screen. We can.
Yes, I have to share my screen again. There we go. Okay. What's interesting is to see what happens if you go from one region to another. So here we go from a global max to no critical points. At this point right here in transition, this maximum here goes off to infinity. And therefore, there's no global max. When I go beyond this region, then you see one of the previous pictures, but there's no max at all, the global max. Interesting point is this one right here. So what happens if I go from a global max to a saddle point? Something drastic must happen at this transition point, and that's indeed the case. So here's again the two pictures. Left-hand side is my saddle point, and at this point here, I get this picture right here. And although it's hard to draw in the picture, here is an arc of critical points. So I get a non-compact family of solutions to the prescribed Ricci curvature problem. That's a phenomenon that you will never see in the Einstein case. In the Einstein case, a modular space is always compact. But in this case, that is not the case, because this kind of, which illustrates that this kind of compactness condition, the so-called Paley-Smale condition, does not hold. In the picture on the left, I want to illustrate how do I prove that a saddle point exists. So I draw this kind of plane here, a level curve. So that's scalar curvature equal to constant, some constant c, just below the limits at infinity. And then I look at what does the region in this plane look like where the scalar curvature is c, and we see two components. There's one component right here, another component right here. These components I can connect. So the first thing that I have to do is find this plane. Let's forget about the picture. Like this is now a general kind of proof idea. Find some plane where you get two components for the scalar curvature. Once you have that, if you have two components, when the space is connected, I somehow connect them with the path. And now I try to move the path up and see if I can. You can never move it past the black plane because it's disconnected. So it has to always stay, a portion of the curve must always stay below the black plane. It must remain hanging on the critical point. That's the goal. One of the problems is that at these points at infinity here, these points cause problems because of the failure of compactness condition. So one has to be careful in constructing these curves here. These initial curves have to be constructed carefully so I can push up with the gradient flow to produce my critical point. So that's what we did in this previous theorem in order to produce the global maxima in the middle here and the set points in this own region. Okay. So that's a typical example of when and how one gets the global max and how one gets a saddle point. Now I'd like to give the problem some more structure, which one can then illustrate the behavior of infinity that we saw in some of the previous pictures in a more uniform fashion. The constraint that we have for this problem was the trace of G must be equal to 1. So for the metric, that would be summation Ti divided by Xi equal to 1, if Xi is a metric. I do this for the inverse of the metric. So I just replace Xi by Yi, and now the constraint simply becomes a linear constraint. And I can define a simplex. So this constraint here, simply look at this constraint, trace equal to 1. Y must be positive. And T is my prescribed tensor, and I always assume that the components Ti are positive. My tensor is positive definite. So this gives you a simplex. So I get a simplex. And when Yi goes to 0, that will be the infinity in the space of metrics. So these kind of sites here, the infinity in the space of metrics, which you can see in the boundary of the simplex. The boundary of the simplex, when some of the wires vanish, they're stratified. Right? This picture, you see a clear stratification. In general, I look at a strata associated to any subset of the index set. So choose a subset of the index set 1 up to S, and look at the points in the simplex where Yi vanishes. So it gives me one of the faces, so let's say, of this stratification of the simplex. So for each subset, I get a face, and the thing is stratified. Yeah. So in this example here, I had 6 strata, the 3 faces and the 3 vertices. And now the important observation is that this has a marking. So remember, the subgroups are important. So somehow, how do the subgroups enter in this picture, in this simplex? They enter in terms of a certain kind of marking. I mean, one proves the following. So it's one of the first thing one proves, which is very important. Assume the scalar equation does not go to infinity. So it's bounded from below by some positive or negative number. That means that you will recognize a subalgebra. So then I look at the direct sum of my subalgebra J, and those summands, so there exists a set J inside I, such that this direct sum here becomes a subalgebra inside G. So I recognize subalgebras by looking at directions at infinity which don't go, which are bound, which are don't go to minus infinity, which go to some kind of finite value. So then I can look at, I can denote this by a strata which has a subgroup associated to it, right, coming from this construction. This, it also has a marking because I have the constants alpha k and beta k I discussed before. Remember, alpha k was a limit at infinity, and beta minus alpha was the slope, the derivative of infinity. So this kind of structure of the simplex together with this kind of marking gives you a lot of information of what you know about what you want to know about the problem. So let's look at some of the previous examples again. Simplex here is two-dimensional. The vertices are strata corresponding to 3 U2s. There I see my alpha with these limit points. My betas was a derivative. And I know for the subgroups, so these are infinity strata. And in the picture, you can recognize this, right? So in this, here's my infinity strata. The boundary of my triangle is right here. Scalar curvature goes to minus infinity along this side, along this strata. Here goes to minus infinity along this strata. Here's a finite value, and it has data associated to it, the value of infinity and the derivative. Here's another example where part of that is better illustrated. Homogeneous space is S3 plus S3 divided by S1. This was still the Wolof space. And here stratification looks like this. One vertex is a T2. Then the strata here is a S3 cross S1. And here S1 cross S3. That's an infinity strata. The vertex and infinity strata. Infinity strata. Here you can see the two torus has limit 0 as predicted by the canonical variations. Along this infinity here, along this edge here, which is my infinity, one of these infinities right here, you can see there's a finite limit for each point approaching the boundary of the finite limit, which has a certain maximum. This maximum is my alpha k. That's why I maximize the scalar curvature over the fiber to reach the highest point. And now the derivative in this example is positive, so indeed I get a critical point. So these markings and the picture that I can draw in this kind of fashion, they tell you a lot about the behavior of the function. Of course, you discuss this kind of behavior in general, right, for any homogeneous space, and you want to prove some kind of general theorem. This example you just illustrate the kind of things you're looking for. Let me maybe just describe a little bit what does this function look like. I'm not going to do any proofs, but how complicated is it to prove theorems of this type? So what one does in general is one looks at the space of all symmetric two tensors. One looks at the subset which is at H invariant. So the subset is in a homogeneous space on G mod H. Inside there, I have to look at the ones which are positive definite. So these are the metrics on G mod H. Then I have the constraint, volume 1 or trace equal to 1. Okay. And now I can ask what is the, how do I describe the metric? Well, you split the perp into, you do the summons with respect to at H. And on each one, I let the metric be a multiple of some kind of background metric. Typically, choose any pi-invariant background metric and scale the metric with respect to some variables in each one of those. So I get an S parameter family in the space of metrics. In general, things can be more complicated because these summons don't, the space of metrics looks like this only if these summons are all inequivalent, which typically is not the case. But this is the simplest kind of situation. So then here's a scalar curvature function that one gets for these kind of metrics. These numbers here, they're structure constants that depend on G mod H. The DI are the dimensional models. Looks somewhat innocent, that functional, but it's very difficult to prove anything about these functionals. For example, this proof by Christoph and Mackenzie Rang that I proved, we were never able to prove directly from this kind of expression, the compactness condition, the Palais-Smith condition. There's no algebraic proof, although the function looks really simple. It's kind of surprising. I can also, if I look at the critical points, here's the equation that describes the critical points. All I have to do is solve this system of equations. Einstein case is lambda, and the prescribed curvature is Ti. So it's a system of S equations and S unknowns. Algebraically almost impossible to study. There are a bunch of papers that solve these equations for S equal to 2, 3, or 4. As soon as you go beyond that, it becomes impossible. And these papers only find explicit solutions. So we want to have a general understanding of the solution. So this kind of equations are somewhat hopeless. But of course, in examples, the way I draw the pictures, I use these kind of solutions and to draw the examples. So maybe the last one I want to discuss is a more complicated kind of homogeneous space where some new issues arise that we're going to see. It's the Stiefel manifold, so 2 frames in R4. So as a homogeneous space, that's SO4 divided by SO2. Okay. So because the SO2 is one of the block embeddings. Here's my SO2, say, here's identity. That's my embedding. Intermediate subgroups, I have now 4 intermediate subgroups. The maximum torus between SO2 and SO4, that's certainly one of the intermediate subgroups. I also have a U2 inside, in between SO2 and SO4. In fact, 2 different U2s depending on which complex structure I choose. They're conjugate by an outer automorphism, but not quite common. And then there's another one, an SO3, simply the SO3 that is a block, which has a block embedding like this. That's my SO3 that sits in between. And now what makes this example more interesting, more complicated, is that the decomposition is not unique. So this kind of formula here that we have here is not sufficient to understand the function. This is too simple, so to say. I have a family of metrics like this, of these kind of what I call diagonal metrics, for each decomposition. If I were to write down the general formula for the scalar curvature without fixing a decomposition, it would become horribly complicated. So I have a 2-parameter family of decompositions. There also exists these SO3s here, they are a 1-parameter family of SO3s in between. So as far as my markings and the simplex are concerned, what happens? I get one nice simplex, which corresponds to the marking U2, U prime 2, and T2. Infinity strata, infinity strata, infinity strata. There's a 1-parameter family of decompositions where my marking is 1 SO3 and the rest are infinity strata. Then there's a bunch of decomposition where everything is in infinity strata. So I get a 2-parameter family of such decompositions. In each case, I have a formula for the scalar curvature, and I have to understand how are they mixed together in order to control what happens with the functional. So for the global maximum theorem, that works in this case. And maybe as a last thing, I will illustrate a little bit what happens with the global maximum in this kind of example. First, to show how complicated it is, here is in this Stiefel manifold, the formula for the scalar curvature, just to scare you a little bit. So my metric depends on 4 different constants. I have off-diagonal entries because in the decomposition of H perp, so H perp is equal to R plus C plus C. I have 2 equivalent summands. These complex summands are equivalent. So I get off-diagonal entries in my metric. Similar for the prescribed tensor T, I get these 2 off-diagonal entries. And here's the full formula for the scalar curvature function. Of course, for my problem, I also have to, in addition, incorporate the constraint that the trace is equal to 1. For example, I could solve for x0 and substitute, and then I get a horrible function in terms of 4 variables, depending on 4 constants that I would I choose ahead of time arbitrarily. So algebraically really impossible to understand. And I've tried this in Maple a little bit. It can't solve it, just crashes. But here's what our theorems say in this case. So here's a picture. So this up here is supposed to say SO4 not SO2. It's also equal to SO2 plus SO2 divided by a diagonal circle. But that's not important here. So here's a picture of T1 and T2. And the variable T0 I set equal to 1 as my scaling. And in this picture here, I assume the simple case where T3 and T4 equal to 0. Now I ask the question, when does a problem has a solution? When does it have a global max? And which group guarantees that the global max exists? And here one sees the feature in this red region, the U2 gives rise to the global max. So it has, in the sense that it has a highest level and it has a positive derivative. I can't draw a picture anymore, of course, but that's what I would imagine corresponding to these previous pictures. That's my highest level here. It has a positive derivative. The other groups, remember there was a U2, a U prime 2, an SO3. They have smaller levels in this kind of red regions. In this green region here, well, let me first talk about this one here. In this blue region here, SO3 wins in the sense it has a higher level and it has a positive derivative. Now remember here, there's a 1 parameter family of such subgroups. So if I were to be able to draw a picture, we'd see this a circle at infinity, where the scalar curvature has different values at each point on the circle. I choose the largest point on that circle and see is the derivative possible or not. That's what happens in this blue region right here. These other subgroups have a smaller level and they possibly have negative derivative. What happens in let's see. Okay, so here in this region, I could say something else. So SO3 gives rise to my global max. I can also look at, so in this case here, I have a normalizer of T, not T that acts on the axis of the problem, which is a 2 torus in this case. The fixed point set of this action on the space of metrics are the diagonal metrics. And in this region right here, I also get a global max from the diagonal metrics from one of the U2s. Here I also get a global diagonal max from one of the U2s. In the space of diagonal metrics, where I set G3 and G4 to 0. Yeah, here I get a global max, and here I get a global max from these U2 subgroups. I can now look at these critical points in the space of all metrics. So now assume that these variables here are an x3 and x4. Now can you look at the space where these variables are not equal to 0 in the full space of metrics? It turns out this is a saddle point. Here the Hessian has 2 positive eigenvalues coming from the diagonal metric and 2 negative eigenvalues in the space of all metrics. In this little region right here, it has 4 negative eigenvalues. So here the diagonal global max is a local max in the space of all metrics, whereas the 3-dimensional group here guarantees a global max in the space of all metrics. One thing I was hoping for, but I haven't found that yet, is that maybe in this region right here, one might be able to find an example of tensor T, where you have a global max coming from the SO3, a local max coming from the U2, And of course, if that exists, if I have a local max somewhere and a global max somewhere, then of course there must be a saddle point. So I'm looking for an example. I'm sure these exist. Maybe in this case, otherwise in general, of an example where you have global maxes, local maxes, saddle points all mixed up together in some kind of interesting way. And of course, if this local max really exists, one has to then work and try to prove the existence of a saddle point, which is not easy. Okay, maybe I should finish here. Thank you.
Thank you for a really fascinating talk. Are there any questions? Ramina? Oh, that's an applause, I'm sorry. So in that situation where you had that sort of whole curve in the first part of the talk of points, what's that correspond to? Does that have an interpretation or?
Or the curve of critical points?
Yeah. Mm-hmm.
Well, it's the, let's see, I can find it. Here's my interpretation. I'm moving from the global max into this region of saddle points. So as I go from a global max, so we had these pictures before, right? There was a global max somewhere. And to the border of the triangle, the max goes off to infinity. And then after that, it becomes a saddle point. How does it do that transition from a global max to a saddle point? There's a curve where the scalar approach is constant. So it's this kind of transition that we would kind of maybe expect, but wouldn't have to happen, but maybe expect as if you go from a global max to a saddle point. But that this is a non-compact multispace, that's what's kind of surprising. This is my example in that for that aspect.
Wolfgang?
Yes.
Yes, about the last example you asked.
Yes.
In the Einstein case, do you know an example with the local max and the global max different?
Well, there are no global maxes, so the scalar curvature goes to infinity unless H is max in G.
Well, two local max different.
No.
Really?
I don't know any example.
Oh, okay. Thank you.
If they exist, they would exist by accident. Right? They wouldn't exist for topological reasons. So topology is this the graph theorem and the simplex theorem for the distance of saddle points. Right? They're forced upon you in some sense. And other type of critical points like a local max, they could exist sometimes. Well, for example, the symmetric matrix is sometimes a local max. I drew this picture here. Where was it? Where this was not the case, kind of a very. I like this picture right here for the symmetric space. This was not a local max, it was a general saddle point. There's another symmetric space where you get similar pictures where indeed the symmetric space is a local max, but the scalar curvature still goes to infinity. So there are examples like that, but they don't exist for variational reasons. They don't exist for global reasons. I don't know one where you have two local maxes. That I don't know. They probably exist, but we have to look at some complicated space where you can't compute the Wickle points anymore. So I don't know how one would be able to predict that they exist. I don't know.
Thanks. Right.
Other questions? Well, if not, thank you again for a really nice talk.
Thanks for listening.
And our next talk is in 2 weeks. It'll be Jia Pan.